This is chapter 3.2. We're going to try to start graphing polynomial functions. So our first objective is to determine the end behavior of a polynomial function. Then to identify zeros and multiplicities of zeros, sketch the polynomial function, and apply the intermediate value theorem. Our first objective is to determine behavior, the leading term test, for a polynomial of degree n, where we have the first polynomial a(n) to x to the n, with all the polynomials in the reducing degree all the way to a to the 0. We can observe the general direction of the function as follows by looking at the leading term. So if the leading term is even, we notice that if a(n) is positive, it will be going up on both ends. If a(n) is negative, it'll go down in both ends. And just think of this in terms of a quadratic. Also, we can look at the odd. If n is odd and a(n) is positive, it goes in this direction. In other words, it goes something like this, right? For a third degree polynomial, that's positive. And if a third degree polynomial was negative, it would go actually like this, right? So in these examples, we're going to use the leading term to determine the end behavior of the graph of the function. So the first function, f of x, is equal to x to the fifth minus 5x cubed plus 4x. When we just look at the first term, x to the fifth, we see it's positive and it's odd. So chances are that it's going to go this direction some way. Right? So that's the end behavior. For g of x, it's got a minus 2 here. And now we see an x to the third and an x to the 1. When we multiply those, we get x to the fourth, and we have a minus 2 in front of it, which means that we're going to have end behavior going in this direction. So our second objective is to find the zeros of a polynomial function. The value of x in the domain of f, for which f of x is equal to 0, are called the zeros of the function. These are the real solutions or roots of the equation, where f of x is equal to 0 and corresponds to the x-intercepts of the graph of y is equal to f of x. So our zeros here in this particular function, if you recall, is x is equal to 1 and x is equal to a minus 2. Those are called the zeros of the function. And they intersect the x-axis. So in example 3, we're going to determine the zeros of the functions defined by f of x is equal to x cubed minus 5x squared minus 16x plus 80. Now when we look at this, we can use a grouping procedure because we have an even number of terms, and we're going to try that. So when we group, we're going to group the first two, and we're going to group the last two, but then we have to change this to a negative. Now we can start pulling out a x squared from the first one. So this is going to be x squared times x minus 5. And in the back we're going to pull out a negative 16. And when we do that, we get an x minus 5. And so this now becomes the following, we get x squared minus 16 times x minus 5. And now if we set this equal to 0, we can find the zeros, right? So this is x minus 4, x plus 4, x minus 5, right, equals 0. And my zeros now are x is equal to 4, x equals minus 4, and x is equal to 5. So there's my zeros. So in practice skill 2, we would like you to do this. You would pause the video and then try to do skill practice 2. Find the zeros of the functions defined by f of x equals 4x cubed minus 4x squared minus 25x plus 25. So here's the answer. F of x is equal to 4x cubed minus 4x squared minus 25x minus 25. They are grouped. And then we factor out a 4x squared from the first one, and we get 4x squared parentheses x minus 1 minus 25 parentheses x minus 1. We see that the first one is now 4x squared minus 25 times x minus 1. And now we have the difference of squares, so we have 2x minus 5 times 2x plus 5 times x minus 5. Now we're going to set that equal to 0, and when we do that, we get the zeros down here. Again, we want to have you try the next function. So find the zeros of the function defined by f of x is equal to x cubed plus 10x squared plus 25. So please pause your video and try this particular function on your own, and we'll get back to you and show you how this one works. So here we start out with fx is equal to x cubed plus 10x squared plus 25. We're going to take an x out. Since we only have 3 terms, we can't really do by grouping, but we can take an x out. We get an x squared plus 10x plus 25. So now we get an x times, and now this thing is factorable. It's x plus 5 squared, right? So now we can set up a 0, x times x plus 5 squared. And this implies that x is equal to 0, and x is equal to a minus 5 with multiplicity of 2. The multiplicity comes with the power of the square term. So this brings us to the multiplicities of zeros of a polynomial function. If a polynomial function has a factor x minus c that appears exactly k times, then c is a zero of multiplicity of k. So in example 4 we have the following. Determine the zeros and their multiplicities. So in this case I set 0 is equal to 8x times x minus 1 squared times x plus 3 cubed. So x is equal to 0 with multiplicity 1. X is equal to 1 with multiplicity 2. And x is equal to a minus 3 multiplicity of 3. So here's our multiplicities, right? We don't have to always write them down. In fact, we won't be actually writing the multiplicities down, but we'll be using them to graph. So, our objective 3 is sketching a graph, the touch points and the cross points. If C is a 0 with odd multiplicity, then the graph crosses the x-axis at C. If C is a 0 of even multiplicity, then the graph touches the x-axis at C. So for example, if I have a function where it looks like this, we can see at this point it crosses the x-axis, and here it touches. So this has to have a squared term at least. This one has to have an odd degree to it. So now, what effects do the multiplicities of the zeros have on the following graph? Note how the lead term changes behavior. So when we look at this, we know what the lead term is. The lead term is x cubed, and it's positive. So you'll notice that the end behavior, right, is this way for this odd function for this. And notice that the zeros are, the zeros, x equals 0, x equals 1, x equals minus 3, and notice there's no multiplicity here, or the multiplicity is 1, so it crosses each one of those points on the x-axis. Now let's take a look at the second one. H of x is equal to x times x minus 1 squared times x plus 3. So again, we notice that the lead term is x times x squared times x, which is x to the 4th, and it's even, so the end behavior is going to go up. And now we can find the zeros. The zeros is equal to 0. X is equal to, oh look at this, 1 with multiplicity 2, that's even. And then we have x is equal to a minus 3. So it crosses the x-axis at minus 3 and at 0, but then it touches at 1. And you can see that right there. So here's our next example. What effects do the multiplicities of the zeros have on the graph? Note the lead term changes behavior. So what I would like you to do is pause this and see if you can find the answers to the multiplicities and find out where they touch and where they cross, and then we'll go through it in just a second. Okay, so we notice that the lead term is x to the 4th. It's positive, so it has to go up, as you can see. And then the zeros is x is equal to 0, x is equal to 1, multiplicity 1, and multiplicity 2 is x is equal to a negative 3. So you can see at a negative 3 we're going to touch the x-axis, but we're going through the x-axis at 0 and 1. So in this example 5, f of x is equal to a negative 3x squared times x plus 4 times x minus 7 to the cubic. Identify the zeros of the function and whether there is a cross point or a touch point at each 0. So when we look at this, we're first going to look at the lead. Let's look at the lead term. First of all, we have a negative 3 out there. Then we have an x squared we have an x and an x cubed. So an x cubed, that's the fifth, so that's x to the sixth power. So the behavior is down for both ends. Now let's find the zeros. The zeros are x equals 0 at multiplicity 2. We have x is equal to a negative 4, multiplicity 1. And we have x is equal to 7 at multiplicity 3. So at 0, it touches. At x, at both negative 4 and 7, it crosses. So turning points. The turning point of a polynomial function are the points where the function changes from increasing to decreasing or vice versa. The turning points correspond to points where the function has a relative maximum and relative minimum. The graph of a polynomial, a function of degree n, has at most n minus 1 turning points. So, for example, given the maximum number of turning points for this function, we see that n is equal to 3, so the maximum turning points is equal to 2 because it's n minus 1. And sure enough, here it is, right? There's the turning points. So we're going to go through the graphing of a polynomial. It doesn't always have to be exactly in this order, but these are good ideas to have. Use the leading term to determine the end behavior of the graph. Determine the y-intercepts by evaluating f of 0. Determine the real zeros of f and their multiplicities. That is, these are the x-intercepts, so we did the y-intercepts and the x-intercepts. Remember, I told you that was important. Plot the x and y-intercepts and sketch the end behavior, kind of. Draw the sketch starting from left end of behavior. Connect the x and y-intercepts in the order that they appear from left to right. This you can kind of do in that order. Remember that you cross the x-axis if a 0 is an odd multiplicity, and it touches but not cross if the 0 has an even multiplicity. Remember, you can always use symmetry in certain conditions, especially with even and odd functions. That doesn't always happen, but if you have that, you always want to use that capability. And finally, you can always plot more points to get a greater level of accuracy. In particular, to estimate the location of turning points, you'll have to do that. Finding several points between two consecutive x-intercepts, essentially. Well, now we're going to do some more examples. So now we're going to sketch the function f of x is equal to x minus 1 times x plus 3 times x minus 4. The first thing is we're going to look at the leading term, so the general shape. That's what we mean. And the leading term here is going to be x to the 4th, and it's positive, which means that the end behavior is up at both ends. So now it says, well, how many turns are there? Well, n is equal to 4, so there is a maximum of 3 turns. Intercepts, well, we know what they are. X is equal to 1, x is equal to a minus 3, and x is equal to 4. But we have a multiplicity of 2 at the intercepts, so where does it cross? It crosses x-axis at minus 3, 4, and it touches at 1. So now I'd like you to graph this function and pause and see if you can graph it, and then we will do that in just a second or so. So again, we're going to find the x-intercepts. And we know what they are. They are 1, minus 3, and 4. So we will put those in, right, at 1, minus 3, and add 4. Right, the lead behavior tells us that this is going to come up like this somehow, and it's going to come up like this somehow on the other side. So where's my y-intercept? My y-intercept is when all of these are 0. When x is 0 all the way through, I have a 1 times 3 times a negative 4, which is a negative 12, right? So, oh, I made a mistake here. This is not at 0, this is at 1, because I now have the y-intercept at minus 12, so that's at 0 minus 12. So that's 70. These are each 10, so I have a point right here. Do you see that point? Now, we're going to sketch the graph in just a second. We know that we cross at negative 3, so we have to go down here, right? We have to go down. We're probably going to go to 12, and then we're going to go up through 1 and touch it. So we're only going to touch, and now we're going to go down again. Now this is where we have to find that extra point in between two places, right? So when we do that, we're going to hold on just a second. We're going to pause. So we have to pause a little bit about our graph, and we see that we've made kind of maybe an error. Even though we know it has to connect from a negative 3 to the negative 12 on the y-axis, we probably should check to see where that connection should really mean. So that means that we need to check some extra points. So we're going to check some extra points real quickly. So the extra points we're going to collect is the following, x and y. We're going to check a negative 2, right? And then we're going to also check probably a, I would check another 3. I would check 3 to see how these points actually work out. So at a negative 2, when we put this in, right, we're going to find the following. So with negative 2, we get a negative 54 when we put it in. And at 3, we get a negative 24. So those are 2 points that we really need to make sure that we have if we're going to do this accurately. So 54 is 1, 2, 3, 4, 5. It's about right here. and the negative 24 is about right here. So now we're going to draw this correctly. We first sketched our graph thinking that, oh, we're going to go like this, and now we're coming up, and now this is the way it goes. Actually, this should touch right here. Right. I believe that's the way it should go. Maybe I'm off just a little bit, but that's the general feel for the function right there. So now we'd like you to try to sketch the next function, example 8. I want you to pause the video and see if you can sketch f of x is equal to a negative x plus 1 times x minus 3 squared. So we're going to do the lead terms, or the lead term actually. In this case it's a negative x cubed, which means that the behavior is going to go in this fashion and down in this fashion somehow at the end. Let's look at the zeros. So this is the x-intercepts. And we have x is equal to a minus 1, multiplicity 1, and x is equal to 3 multiplicity 2. So we can actually graph those 2 points, 1 and 3, 1, 2, 3. And then we need the y-intercept, right? So the y-intercept, well, when I have 0 and 0, I have 9 times 1 is 9, but it's a negative, so it's a negative 9. So let's see, negative 9 would be about right. These are 5 apart, so we're about right here, I think, right? I think that's right. So now I have to draw my graph, and we may pick another couple of points. Suppose I pick a point, say I pick a point at 1. So let me do this real quickly. Suppose x is 1. Then what is y? So if I put 1 in there, I get 2 minus 2, but that's squared. So a minus 2 squared is 4, times 2 is 8, but it's a negative 8. So let's see, we have a 9 and 1 is a negative 8. That's going to be about right here, right? So it looks like this thing, let's try another point. Suppose it's 2. So I have 3 times a negative 1 twice, so 3 times, so that's going to be 3, a negative 3, so that's going to be about right here. So I guess our graph is going to kind of go like this. It's going to come up, it's going to come down. Now it's going to touch here, and then it's got to go down. Remember behavior of our lead term. So that's what the graph looks like. So our final objective is to use the intermediate value theorem. Let f of x be a polynomial function for any a less than b if f of a and f of b have opposite signs. Then f has at least one 0 on the interval of a and b. In other words, if a and b have opposite signs as far as the value of y, then on the interval of x for a and b, we have 1, 0 crossing the x-axis. So in example 9, we want to show that f of x, x cubed minus 13x squared plus 33x plus 35 has a 0 on the interval between a negative 1 and 0. So what we're going to do is evaluate the function at f minus 1 and find out what that value is. And then we're going to evaluate f of 0 and see if they have opposite signs. So when we evaluate at negative 1, we get a negative 12. When we evaluate at f of 0, which is our y-intercept really, it's at 35, right? Because these have opposite signs, there has to be a 0 crossing between negative 1 and 0. So I would like you to do skill practice 5. Show that f of x, where x to the 4th plus 6x cubed minus 26x plus 15 has a 0 on the interval between negative 4 and negative 3. So pause and try the example. So here's our answer. We have f evaluated at a negative 4. We get a minus 9. When we evaluate a negative 3, we get a 12. We notice that they are opposite signs, so that means there must be a 0 between a negative 4 and a negative 3 in this function. So what did we learn? Well, in this chapter, we looked at graphing polynomials. In particular, we're going to find the x-intercepts, which is the zeros, the y-intercepts, the ending behavior, and then for x-intercepts, do they touch or do they cross, right? And then in between, when we're graphing the graph from left to right, we check extra points. So check extra points for accuracy. Alright, so that concludes our section 3-2. Please work some additional problems in the book and go through the problem sets of the day.